gets constructed, it is basically the rules which actually split the data into multiple conditions, multiple parts, and ultimately we reach to a part where everything belongs to one class. That's the pure nodes, leaf nodes. Okay. So in this particular example, we try to split the data using ID3 algorithm like this. So train set is split into a tree, and then it is being saved into a memory. And then when a new record comes in, we follow through the conditions, right? The first node is going to be on outlook, and we see where it is going, and second node is going to be on humidity or wind, right? Like that, we actually traverse through and reach to a place, and whatever the ultimate leaf belongs to, if it belongs to all S's, we'll say it is yes. If it belongs to all no's, we'll say it is no, right? So that is the tree construction. So, but to build this tree, there must be some criteria, some way to choose the best features to split on. Right? We cannot split on any column and then reach to a optimal leaf node, right? So to choose that, we have two metrics: information gain and Gini gain. So in Gini gain, a different formula; information gain, another different formula. Gini index is the metric which ultimately results in Gini gain. So Gini index or information gain, both are impurity measures. Right? Impure, less impure, that's the best feature. Impurity means will not be able to distinguish the target class using that particular class, or may not be that clear in distinguishing the target variable. And that bags example we have seen, right? So when there is more uncertainty in the data, when you try to pick something, you don't know, right? You will not be able to decide which. So that is the impurity measure. So we are using impurity measure to decide on which feature to split. And then we have seen how the decision trees are prone to overfitting. Because if you look at this data, in this particular data, there are 36 combinations, 36 possible combinations, but in real time, all combinations may not happen. We have 14 combinations here. Maybe out of those possible combinations, I think I have taken one combination here, which we may not be able to predict using this particular tree. Right? That means data will the algorithm, the model, the tree model will work well, 100% well for the training data. Right? If you built the tree till the leaf nodes, right? If you decided to stop at maybe second level or third level, this first level, second level, third level, maybe the second level or so, even on train set it may fail, right? So in some cases, but it may actually predict on the test set also the similar way, right? It is like overfitting. How will you adjust? You will make the model a little weaker. That way it works well on the, it works a little less on the train set and similar on the test set. Some scenarios will get covered. Okay, so that's the overfitting, right? Why overfitting happens on a train set, we know. And then the information gain and Gini index both have some drawbacks, right? So they actually favor the features with the multiple attributes. So if you have two distinct attributes, you should eliminate those and then use the decision tree model. Rather, it's going to get stuck. It will work well on the train set, 100% on train set, and 0 on test set and production. So that's a key point we need to remember. And to avoid that problem, there is a formula called the information gain ratio. But some algorithms use this, especially in the R language. The C 4.5, C5 implementations are there. These are the versions of the ID3 algorithm. These are different versions of the ID3 algorithm. And the what you call it as scikit-learn uses CART algorithm, which is a binary split. This information gain ratio has got a split info, a formula, which tries to assign a big number to the features, right? Which actually results in a this formula results in a big number to the features which have got more distinct categories. That way, ultimate gain ratio on which the algorithm makes the decision to choose a feature is going to go down. So whichever gain ratio is high, that feature is going to be the best feature. So this formula helps in that way. But this formula's drawback is it always tries to split data into unequal partitions. Wherever there is unequal partition, that way it actually fails. But this is better than the information gain and gain ratio. Sorry, Gini index. Okay, so that far we covered yesterday. And today, right, we will look into overfitting and underfitting problems. More overfitting and underfitting. So decision tree, overfitting, and pruning. So pruning means cutting the branches, right? So if you look at this graph, this is from book I forgot, machine learning. Give me one second. That that book, no, that's a famous book, from long back. Machine learning. Yeah, this guy, this book. I have a hard copy of it. So Tom Mitchell. Okay, this is a famous book, right? This is a famous book, but it's a theoretical one, and it starts with tree-based algorithms. Okay, so why am I pinpointing that? It starts with the tree-based algorithms. Is that when you want to go into deep depths of AI, you should start any book should start with linear regression, logistic regression, and gradient descent algorithm. Right? Some book is starting with a tree-based algorithm that maybe they are focused on only machine learning algorithms, don't want to go into deep learning. That's where we started with the linear regression, logistic regression stuff. Okay. Some people in the courses also they do this. They start with tree-based algorithms and try to go into whatever, but you will not touch depths of AI. Okay. So that's that's out of whatever, but I wanted to show you some the books I referred to. Okay, so this is a Tom Mitchell book, the whatever, right? And then if you look at y-axis, this is accuracy, and x-axis size of the tree. With the size of the tree increasing, the accuracy on the train set, right? The straight line, the solid line is a train set, train data accuracy. Dotted line is on the test set accuracy, right? Where with the tree size increasing, the number of nodes increasing, right? Number of nodes is nothing but tree size, right? If the tree size increases, nodes increase. This is first node, this is second node, third node, fourth node, like that. Number of the tree size increasing, the accuracy on the train set is increasing, but the accuracy on the test set is decreasing. Right? In other words, if you say, right, this if you build complete tree, right, with all the end nodes belonging to a particular category, right, you prune, you actually not prune, you actually try to traverse through whole data and try to create perfect tree. That will work well on the train set, but may not work well on the test set. Right? So there is a trade-off between the um, bias variance trade-off is there, right? So you try to reduce the overfitting, the model will become a little underfitted, right? High variance, this is high variance model, right? This is high bias model. In between, right? You are choosing something. So you are reducing the power of the model in such a way that it may not work on the some of the train set data, and it works equally well on the test set data. So somewhere here you need to choose. The tree size should be 10 here to make the model best. So the overfitting, right? This is called as pruning. You try to chop off some of the branches in such a way that it works well on the train set and test set. So some of the the decision tree split data until it ends up with pure sets, right? Decision trees split data until they end up with pure sets. If you leave them, with their default behavior, this is what they do. This is what they do. Okay, you can actually control that. Okay? There are different ways of controlling it. Why do you need to control? If you build complete tree, it will overfit definitely. Okay, sometimes it splits until leaves have one example. This is not good, right? If you see here, some of the leaves have only one leaf. Right? This is not good. Right? That way shouldn't be, that tree shouldn't be splitting. What is the problem? If it splits like that, it's going to be overfitted. Okay. Give me one second. Okay. And with size of the tree model overfits the train set, overfits on training set. Okay, overfits on training set is the right statement. I don't know whether you noticed it or not. Overfits on train set. Okay, it understands well on train set and fails to generalize. Okay, so how to avoid overfitting? That's the key thing we are pre-pruning. Okay, do statistical significance test, chi-square test on the split and stop if not significant, right? What is the statistical significance test give you? What is the outcome of a statistical significance test? What is the outcome of a statistical significance test? Guys,
accept or reject hypothesis.
null hypothesis, right? Accept or reject null hypothesis. The null hypothesis on building a tree is that, how do you do that? You have original data, right? You have original data where you have y variable, and you try to build a tree with maybe two branches like this, maybe only only three branches like that. Okay, and then try to make predictions and use the predicted value and actual value, right? They both are categorical values, right? Categorical columns, and do chi-square test, right? Chi-square test will give you p value. Where is that? Yeah, here. Chi-square test will give you a p-value that actually shows you if it is greater than 0.05, it is not significant. Split is not significant, right? You can accept null hypothesis. The null hypothesis is split is not significant. We'll accept the null hypothesis. If it is less than 0.5, 0.05, we say it is significant, right? So like that, you need to, on every split, you need to make predictions and calculate chi-square p-value and then decide. Is there an algorithm that does it? No, there is no implementation for this. But theoretically you can do that. How to avoid overfitting. Theoretically you can have this kind of uh, model, this kind of implementation. In R language, we have very powerful models for tree-based algorithms. But in Python, we have very powerful, deep learning algorithms. That's where I never touched R language in my career so far. I learned it, but I never used it in any project so far. Okay. So pre-pruning is like before you split the tree, you understand whether the split is significant or not by doing statistical significance test. That's where you call it as pre-pruning. With using that, you can build a tree that is balanced on the train set and test set. Only when it is significant, we are making the split. Rather, we are not doing it. Post pruning. There is another way. You build complete tree like this. Right? Like this, you build complete tree. You try to chop this off and try to make predictions. See how the model is working on train set and cross validation set. If it is working well, right? You chop it off and take the rest of the tree and use it. again you chop this off, and then again try to test. If it is not working well, you keep this, right? And you need to keep this also, that whole whatever branch you need to keep. Now you chop this off, and then try to take the tree and test it. If it is working well, you chop it off. If it's not, you again attach it. Like that, it post pruning. Post pruning is like you cut it and test it, cut it and test it. If it is not working, you just rejoin it, reattach it. If it is working well, you cut it and leave it, right? So that's how the pre-pruning and post-pruning techniques will work. Okay, and there is another way is called as cost complexity pruning. So this is like regularization. Okay, so if you look at these two diagrams, right, you will understand what I'm actually trying to explain here. Cost complexity pruning, how it works, as known as weakest link pruning, gives us a way to do just this. Whatever this um, post pruning activity we are doing can be achieved by using cost complexity pruning. The overfitting is directly proportional to the depth or number of leaf nodes of the tree. This is the key point. Right? Depth or number of key, depth means how many levels are there. That is depth, and how many leaf nodes. To both, the overfitting is actually directly proportional. The cost complexity pruning focuses on number of leaf nodes. As for some trees, depth may be same, but tree may be complex. So the height may be same of the tree, but number of leaf nodes are more in one tree, and another tree the number of leaf nodes are less. Based on that, it may be overfitting or underfitting. So there is an equation like this for the cost function. Whatever the error we are getting, right? If it is a regression metric here, classification metric, plus alpha into L of t, right? Alpha is the tuning parameter. L of t is the function measures the number of leaves in the tree. So number of leaves are here 1, 2, 3, 4, 5. In this 2, right? Here for this tree it is going to be 5. For this tree it's going to be 2. Right? Now if you make alpha is equal to 1, but alpha is equal to 0, right? It's a standard learning tree. Whatever tree you have, that's the tree it's going to build. If you take this alpha a big number, what happens? Cost is already too big, so it will try to reduce these number of leaf nodes. Automatically the leaf node reduction will happen. So you play with alpha, the model will come to a stage where it is balanced. So it is an automated approach to balance the tree, or post pruning approach, right? Automated post pruning approach is cost complexity pruning. Okay, so in our scikit-learn, do we have all these parameters? No. There are two variants, decision tree classifier and decision tree regressor. I'll actually explain you. So here, right, criteria, either you can use Gini or entropy. Gini is the Gini index, entropy is the whatever that information gain. Okay, information gain. And splitter, right, random or best, right, best split. Best split is the default. Best split is like, it uses this metric and tries to calculate. The strategy used to choose the split at each node. Suppose supported strategies are best to choose. Let's try best. Yeah, based on this calculation, right, it will choose whatever the math I showed. That's the max depth. Now you can decide how many layers it should have, min sample split, right? If you want to split a node into two or three, right? If it is a ID3, right? You may be doing multi-way, right? More than three, right? Whether you want to split a node or not can also be decided, right? If you have, minimum number of default is 2. If you have 2, it will split it. If you say this has 10, it will not split the tree. That even though the node is not pure, it will not split if the number of data points in that particular node are less than 10. Okay, So like that minimum samples you can specify. This actually constrains, right? This and this constrains the tree height, right? When the model is overfitting, those hyperparameters are useful. See this here. If the number of nodes are more or the depth is more, the model is overfitting. So if the model is overfitting, you need to play with these hyperparameters: max depth, min sample leaves, min sample splits, min sample leaves. Right? In a leaf means what? The ultimate end node, right? How many samples should be present in that? So in different ways you can control. Okay. So there are different hyperparameters here, but not the cost complexity pruning. I think they added this one new thing. Cost, complexity parameter used for uh, yeah, minimal cost. So these guys added it, right? New in version 2.22. Previous versions this is not there. CCP alpha, right? What is the CCP alpha? I think you cannot you can actually avoid using these min samples, max samples, and now you can play with this CCP alpha, which will actually try to CCP alpha will actually try to automatically control the leaf nodes there, right? See this here. If you take this alpha a big number, the tree is going to become like this. All the leaf nodes and other nodes will actually chop off, right? And then it will become the start node or whatever. So alpha is equal to 0, the standard learning tree. Whatever tree you learned, big tree is going to come. Alpha is equal to infinity, then root node with a lot of prediction errors, right? Root node with a lot of prediction errors. Only the main data set, and then only 2 branches, 3 branches, but you will not be able to predict well. Okay, need to find an alpha between 0 and infinity. We can select value of alpha using validation set or cross validation score, right? You use CV or grid set CV, right? Pass different alpha values, run the code, it will find out the best alpha, which will actually try to decide the height of the tree. Okay, that is more convenient, right? This was not there before, and I was very disappointed, but now we have it. Okay, so on a binary tree, it is going to be balanced, and you can actually specify other things also. See this, whenever it is trying to balance, right? N samples divided by n classes into np dot bin count. I don't know what is bin count of y. Bin count. Okay, different categories are there, right? How many categories are there? Okay, so n classes, number of classes, and bin count. I don't know what this is. So it's going to calculate this kind of a number and multiply this number with all the rows. That's the way it is going to assign weight. Okay. So this is the important thing, right? CCP alpha, cost complexity pruning. Okay. So that is about the tree-based algorithm, and summary I would like to give, and then I'll stop for questions. Decision trees have relatively faster learning speed than other models. Easy to understand classifying rules, right? When you build a model, right, you can actually, this is all if else conditions only, right? So easy to understand the algorithms, whatever pattern recognition. And information gain ratio, and Gini index are the most common methods of attribute selection, right? Impurity measure, or I think gain ratio is a purity measure. Whichever is high purity, we are taking. This Gini index and information gain are impurity measures. Okay. Tree pruning is necessary to remove unnecessary branches. We can use this cost complexity pruning approach. No formal distribution assumption. There is no assumption, like as in the naive based algorithm, we haven't seen it. Naive based algorithm, it assumes independence between the columns, but in here there is no assumption. Or in linear regression also there are assumptions, right? So there are no assumptions. Okay, can automatically fit highly nonlinear interactions. Now, we'll see how exactly the decision trees help you fit nonlinear thing. And then automatic variable selection. Right? I have shown you that, based on impurity, we are choosing the first node, second node, like that, right? So we'll see that code point of view also. We'll see that handles missing values also. If there are nulls, no need to fix them before you build the model. It will automatically, do it. Instability. If you change data a little bit, the tree picture can change a lot. This is the point I was explaining yesterday. Right? If you remove maybe 5, 6 data points from the train set, or add 5, 6 data points to the train set, the total picture will change. Total tree structure will change. Okay. Scalability is an issue for the large data sets. Right? For the large data sets, right, it actually builds everything on in the memory. So it may not fit for the large data sets. Okay. So these are the pros and cons of decision trees. Do you have any questions, or shall I go into the code and then we'll start? I think we'll look at the code and then we'll start for the questions. Okay. So decision tree classifier. So far we have understood theoretically how the decision tree classifier works. I have taken the same iris dataset, right, like this Satosa, versicolor, and Virginica. And the algorithm, right? After building the algorithm, you can actually look at the picture also. There is some method I'll show you, but in real time it's not going to be useful. But for fun, I am showing you. See this here, the petal length. It shows as the first best feature, and then it is measuring less than or equal to 2.45. So in this theory, right, what I said here, I'm actually calculating Gini index and whatever, right? So because these are all categorical columns, I'm calculating Gini index or information gain. Okay. If it is a numerical column, right, you actually try to see this is called as cut point. Okay, on this petal length, right, there are values here. 1.4, 1.4, 1.3. You take all distinct values from this, try to divide the data, right, less than 1.4. Try to see the records falling on the left side, records falling on the right side. Take those counts and calculate the probability. Okay. Again, try to take 1.5, calculate probability. Try to take 1.6. For each column, you will have different cut points. The algorithm will try to play with those cut points and find out the probability. Whichever gives you less impurity, it chooses that as the best feature. Did you get it? Did you get it?
Yes, sir.
Right. In here, it is categorical column. So we were actually able to calculate probabilities, right? Probability, conditional probability, and all that. There is that. Yeah, this is conditional probabilities we are calculating. But on a numerical column, we will take no, on a numerical column, you don't know whether the 2.45 is the best cut or not on this particular column. Again, there are other columns. In each column, there are numbers. But you don't know in which column, which is the best cut. So it is going to experiment with all distinct values. It will take all distinct values, all distinct values, all distinct values. It tries to do all cut points and calculate probabilities, all cut points, calculate probabilities, all cut points, and it finds the best cut point where it gives you less impurity, right? And then chooses that as the best feature and splits the data. It is doing a binary split. See this? Because it's a CART algorithm. Okay. And then no, it actually got all pure node here, all 50 belonging to Satosa only. Here it has got some versicolor, some virginica, I think. And again, it is doing petal width. Based on petal width, it is actually doing a split, and it has got two. So this is the tree. When you pass a new record, right, it looks at a petal length. If it is less than, it says Satosa. If it is more than, right, it will go here and try to look at petal width and then decide. See this here? If you look at the diagrams also, right, this is the petal, right? Petal length less than 0.25, that is Satosa. See, these petals are very thin here, right? So other two, right, there is a different path. So it identified that pattern. If else conditions only are the decision tree. Each node will have an if condition. Based on that, data will be splitted. Based on those conditions, the new predictions will be made. That's the key. How exactly this is chosen depends on whether it is numerical column or categorical column, input column. Okay. We are talking about classifications. Regression also we'll talk about in like maybe 2-3
Sir, can
months.
you come again on the cut point?
If you take this sort of sepal length, all these are numbers, right?
Yes, yes.
So probably there is a best cut point. If you try to split the data based on 4.9, you may get less impurity, right? Right?
How to choose that cut point? You are
That's what I
telling
am
like,
saying. That's what I am saying. It is going to do, you take all distinct values from here
mhm.
and split the data based on first distinct value, calculate probability, second distinct value, calculate probability, third distinct value, calculate probability. Like that, it will do all the probability calculation, keep aside. Again, take this, take distinct values, calculate probabilities, keep them aside. Take distinct values, calculate probabilities. Out of all those probabilities, whichever is less, it is going to choose that column and that cut point.
So
Got
not
it?
clear on calculating the probability, sir.
See how is this calculation is happening here? Probability of Sunny into probability of yes given Sunny, no given Sunny, right?
Yeah.
Right. Like that, probability of data less than the cut point, and
Mhm.
probability of yes given the data less than cut point, no given less than cut point, based on condition. Right. You have count here. Probability of less than the cut point, there is a count, right? And then the total number of records are there, right? And again, there are yeses and nos, or there are 2-3 different classes, right? First class given the cut point, second class given the cut point, third class given the cut point. It will calculate, it will multiply all those problems again for the second column, third column, like that. It's going to be, right? Got it? Got
So
it?
it takes one value and it considers greater than and less than.
Yeah. So on the outlook, right, there are going to be two cuts, right? If you do a less than and greater than, there is going to be one less than for one greater than. There are going to be two terms there. Got it? No? No?
On categorical column, yes, I got it, but on the numerical,
Give me
just
one second.
trying to visualize.
Yeah, it is. Give me one second. Okay. Basically, what we are doing is we are actually making the data set, numerical data set into categorical, right? Let me take a screenshot and try to explain. Suppose there is a data set. I'll take only yes, no. Variable. Yes and no. Right? No, like that. Okay. And then there are multiple columns. Suppose that I have taken for each column, right? There are different cut points. So I am taking a maybe length column. Okay. The length column. In this column, I have 0 0.4, 0 0.5, maybe 0 0.3, 0 0.1, 0.4, like that. Okay. So I have taken a distinct value 0.4 and said, maybe I'll take 4 values there. Right? No, yes. Okay. So now I need to calculate Gini index of this, G of length. It is going to be now there. I suppose that I chose the cut point as 0.3. Okay. So probability of length less than 0.3 into probability of S given length less than length less than 0.3 into probability of no given length less than 0.3, right? Plus in this column, right, there is other set, right? What is that set? Probability of length greater than or equal to L greater than or equal to 0.3 into probability of S given L greater than or equal to 0.3 into probability of no given L greater than or equal to 0.3. So length less than 0.3, probability how many? 1, right? Only 1, right? 1 by 4, right? Do you agree?
Yeah, yeah, 1 by 4.
Right? Yeah, yes given less than 1 given 1 divided by
1.
1, right? Into 0, right? No,
No,
there are no records. Right? This is no. This is yes. I think I should have taken a different color here. I don't know whether it's really visible or not. So 0 plus probability of length greater than or equal to 0.5 is 3 by 4 into S given greater than or equal to 0.4 is 2 by 3 into no given greater than or equal to 0.5 1 by 3, right? So this is the probability for length at this cut point. Like that, all distinct values it will take for length. Length at 0.3, length at 0.5, length at 0.4. Different values it will calculate and keep these probabilities aside. Right? Whichever minimal comes, it will choose that and keep that aside again on this particular column. On the second column also it will do the same thing. On the third column, fourth column it will do. Whichever is minimal, right? Out of all four, it will choose that as the cut point and do that. Does that whatever. If you see here, there is that. Got it?
yes, sir. This is ID3 or the other one?
Cut.
Cut.
It doesn't matter, right? Multi-way split or individual split. That doesn't matter. Any algorithm can use the same formula, gene index or cross entropy.
Okay, the same type of logic applies for the cross entropy as well.
Formula is different. Log
Yeah,
is
for
there.
formula is different.
Minus 5
Yes,
log, yeah, minus 5
but
log. Same,
considering this
yeah, same cut point thing.
cut point.
In regression, right, on the y value also it does the cut point thing. So we'll talk about that in a
Yeah,
few
yeah.
minutes.
Okay. Yes, sir. Go ahead.
Good. So no, that's how the tree actually been split. I think I need to make this a little big. Right. So the algorithm first splits the train set into two subsets. Using single feature k, a threshold. I say threshold or cut point. Right. So like that, it actually repeats. The algorithm searches for k comma tk, the purest subset. The cost function is provided by hyperparameter, right? Whatever the cost function is, that criteria, right? So Gini index or whatever, we actually saw that. Okay, and then these are the hyperparameters. But I think with CCP, cost complexity pruning alpha, we can reduce using these and use that more. You can experiment. I never does that code. I took the data, I splitted data, then decision tree classifier I have taken, and then max depth I have taken 2, and then fitted the model. That's where I got I said 2, right? Only 2, 1 2, only it went to until 2 depth. Right now I built the model, right? I fitted the model, simple, right? Now I know the classes order, I know the probabilities. Whichever probability is high, the record belongs to that particular class, right? So I have kind of built a method to calculate the accuracies, precision score, recall score, and all that. I'm getting 95% accuracy, and then on the test set also I'm getting 97% accuracy. This looks good. let's try, grid set CV. I actually did some, grid set CV stuff here. You guys know this, right? So I'm just, it shows best depth as 5, 6, and max leaves as 8. Now I took the best estimator, and using the best estimator, I'm fitting. Now I've got like 99% on train set and 1 on the test set. So that's the total, decision tree classification thing. Right? Now we can actually start for questions. Go ahead. Sishram, you had some questions, right?
Yes, sir. Here we said decision tree as an algorithm cannot be used, right, as a final model.
Yeah.
So after this, what we do?
We have that. Next class is going to be, right, maybe tomorrow or Monday, right, depending on the time we have. I'll
Okay.
explain you the ensemble models where you actually combine many trees and try to solve that overfitting problem. We are having overfitting because we are looking at the whole data, right? We'll take chunks of data and try to build multiple trees and then try to use that to fix that overfitting. I'll show you. I'll practically show you how exactly that overfitting gets fixed in the ensemble models.
Yeah. So,
Sir, to avoiding the overfitting, we are using the pruning methodology, right, sir?
But what happens is, you are actually bringing down the 100% model to some less, but lesser accurate model. But basically overfitting, you are trying to prune or regularize. This is actually overfitting regularization, right? When you are regularizing, what are you doing? Actually, it can do 100%, but you are bringing it down to 80% on the train set and test set both. You can improve this. You can make it maybe around 90% by taking multiple trees and building an ensemble model.
Okay, got it.
Power we are trying to increase. Here while doing regularization, we are trying to reduce power. By making model, more complex, we are increasing the power of the model.
Okay.
Shashiram Gar, any other questions?
yeah. Sir, on calculating the Gini index of the target variable, can you please go to the slide?
Yeah.
So the Gini index, I did not understand the formula, sir. Can you please go up a bit?
This one.
Yeah. So here it is Gini index sigma I not equal to j. This is considering only two classes, the target classes.
Not
right?
two. If you have more classes, right? If you have 3 classes, right? You will have pi, pj, pk. Multiplication of 3.
Yeah.
If you have 4, you will have multiplication of 4, and then the terms will increase, right? From I is equal to t, t is equal to 1 to k, right? 1 minus p I square, p g square minus p k square, or like that it's going to be.
Okay. Then the formula then goes to sigma I equal to 1 to k p I square.
Yeah. No, it is like 1 minus, if you have 3
One.
classes, Satosa, Virginica, versicolor, 1 minus probability of Satosa square, probability of Virginia square, probability of Satosa square. If you have 10 numbers, right, 0 to 9 in the digit recognizer, 1 minus probability of 0 square, probability of 1 square, probability of minus probability of 2 square, minus probability of 3 square, like that till probability of 9 square, minus 1 minus.
Yeah, yeah. So why this 1 by 2? 1 by 2
Eh,
square.
Here I actually took this binary, right? Binary target variable, right? For binary target variable, maximum Gini index is going to be 0.5. For binary, it is.
So binary, So here, are you assuming that the S and no's are equal?
No. Yeah, equal. Yes. That's what I was about to say. Yeah, yes and no's. In a data set, if you have 50% SS, 50% no's, maximum 0.5. That's the maximum you can get when you calculate Gini index. If it is 0.75 and 25, if you substitute that into this, you will get a little less number than 0.5.
Okay. So how this formula will be transformed when it is uh,
It is if
multi-dimensional? The input for input features. So
there are
Gini index.
four different classes, then it's going to be 1 by 4 square, 1 by 4 square, like that. It's going right
Yeah,
here,
that I got it.
similarly, the normal variables with the k levels, right? The maximum Gini index is going to be 1 by 1 minus 1 by k. This is the formula for that. I think your question is right. If you have three classes, right? 1 minus 1 by 3, 4, 1 minus 1 by 4, 5, 1 minus 1 by 5. There is a lot of math behind this. Right? If you want, you can go. I actually looked at it long back and wrote it, but if we go there, right, we'll get lost in math.
No, I'm not going that depth, but I'm just trying to understand whatever
Yeah,
is.
this is the formula to calculate that. I think your question, I think answer is here, right?
Yeah. The
Is
next
this the
one,
one?
sir. Yeah, I got that one.
Okay.
I did not get that 1 by 1 minus k, but the above stuff like 1 minus 1 by 2 square.
This is if you want to understand this, right, you need to see, you need to experiment with different number of classes data or the formula, and then you will understand. Maybe you need to look into the theory. I used to have a link for this, but I took it out because nobody was focusing on it. So,
Okay.
Gini index. Maybe you can Google. Most of the times we find these things in this Khan Academy also. Yeah, this one I think. Investopedia. Yeah, that's okay. You try to find it. I used to have a link from where I got these formulas. I took it out.
Yeah,
Maybe in the
I will
old
check.
code.
I'll check.
Give me 1 second. Maybe in the old code I'll have it. I'll share that link. I have upgraded the notes a lot. Previously the course was not this good and not this organized. I took out a lot of stuff. Included a lot. Yeah, this one. Oh, link is not there. Right, no more the link is present. Okay, leave it.
I'll check. I'll check some other sources. So the next one is Gini index for input features, sir. This one is actually the first sigma and V.
Ah,
So
give
let's
me
say,
one. No, these guys will not give that clearly. Maybe in the medium. Okay. Okay, let's go. Okay.
Yeah,
So
I will check that. I'll check that. So the Gini index for input few features. So the formula is Gini of A, we are saying. So sigma V is, let's say we take the first feature, that is outlook.
V is the A is the outlook.
Okay,
B is
A is
the distinct category.
okay, distinct category in that.
See this here. Outlook is the A. Sunny is one distinct category. Overcast is another distinct category. Rain is another distinct category. Even in the numerical calculation also, I took less than and greater than as two different
Yeah,
categories. I am actually collapsing the data, right? Less than, greater than, two categories I made and then try to calculate probability for less than and greater than. Try to. So, A is outlook, right? Column is A. I think maybe I should put F in the feature and C in the category. That way it's going to be more clear,
yeah.
right?
But the second sigma, will that be a sigma? It's actually not the summation, right? It's the multiplication.
Yeah, pi maybe it is.
Yeah.
No. If you have, uh, yeah, that's a good question. Second sigma, maybe if you have,
Let's
if you have,
assume this.
yeah, no. I think maybe the sigma is not. Uh, I don't know.
I was actually trying to find out that. Let me just put my thoughts here.
Yeah.
So V is the number of categories in the input feature, number
Mm.
of groups actually. Like
Yeah.
Outlook, we have three groups,
Yeah.
and I and J are actually the categories of the label, the output feature. So
Yeah.
if it is multi-label, instead of just yes no, let's say we have digit recognizer, we have 10, right? So in that case, it will become the sigma is actually becomes pi I equal to 1 to I equal to 1 to 10, and p
Mm.
of c of I by v. C is the class.
I think. Yeah. I by C, I by J by C, something like
Ci
that.
by
P.
Ci by v and ci1 by v. Probability of ci1 by v. Probability of ci2 by v. So C1, C2, C3 are the classes in the target. So
Yeah.
it's a product, right? It's a product. So that sigma, the second sigma looks like not correct to me.
Yeah,
And
maybe. We need to look into that theory again, right? I need to look into that code, that
yeah, the first sigma is actually
math again.
the summation, the category is summation of the input variable.
Yeah.
The first sigma. The second sigma is actually the product of uh, the target categories with respect to each category of each group of the input variable.
Yeah. Yeah. Look at it and let me know. But Narayan garu, don't be worried about this math. We know how it is working, right? And
Okay, sir.
Seshiram is more interested in math. He is looking at it. It is going to be useful, right? In some of the projects where the math is in computer vision projects, basically math is very intense, right? So if you know how it's working, I just focused on how algorithm is actually distinguishing data, how algorithm is working behind the scenes. So if you understand that, that's enough. Don't be worried about this math, but somebody is interested in math, right? They can actually dwell through it because that is also a different capability in AI, right? So in many engineering problems, we have to provide AI solutions where math is going to be a little intense, but those projects are very rare. I would say those projects are very rare. Okay. So and there will
Okay, sir.
be subject matter experts also, and they'll give us the formulas. So don't be scared. You are understanding everything. You are able to write code. You know how the algorithm is working. That is good. Okay.
Okay, sir. Thank you.
Yeah. Yeah, Narayan is always worried about the math. So whatever math I am explaining, if you understand that part, that's good enough. Don't go into details of it. If somebody is interested like Sesiram, right, they can go. It's really a good skill, additional skill on top of whatever we have here. But I would
Yes,
say
sir.
it's rare. It is rare.
Yeah, as you
So
said, I am also not going that detail, but just trying to understand what we have discussed, trying to understand
yeah,
clearly what